Hey guys, so today we're going to do the fundamental theorem of calculus, and we're going to start talking about definite integrals. So, in the previous lesson you were taught how to determine the indefinite integral, which would be the area under a curve from negative infinity to positive infinity. But today we're going to determine definite integrals, area under a curve between two specific x values. We begin with a function f that is continuous on a closed interval between a and b inclusive. The definite integral between a and b, f of x of d of x, area under the curve from f of x, under the curve of f of x from x equals a to x equals b. Okay, so the fundamental theorem of calculus states that if I give you a definite integral of from a to b, a being low bound, b being high bound, of f of x dx, what I can do is I can just find the antiderivative of that, and then I take a, b, and I fill them in function notation f of b minus f of a. And you also have to put this little square bracket where you put that ba. So we're going to go through some examples. So determine the value of the following definite integrals. So here we have between negative 2 and 1, under the curve of x squared, we're trying to find that area. Okay, so let's use dark blue. First thing we're going to do is we are going to do the antiderivative of x squared. The antiderivative of x squared, we raise it to 1 power, x cubed, and then we divide by that number. Divide by 3. Add c. And then we put a square bracket at the back so that we remember what these numbers are, because the integral symbol goes away the moment you find the antiderivative. So we have to still keep those numbers to know what to put in. So we put a square bracket at the back and we put negative 2 and 1. And now we're going to fill them in. We're technically going to do f of 1 minus f of negative 2. I'm just showing you off to the side what we're going to do. And f of x being the antiderivative, right? So 1/3 x cubed plus c. All right, so we're going to go round bracket, 1/3, and now for x I'm going to fill 1 in for all the x's. So I'm going to go 1/3, 1 cubed plus c, and then I'm going to subtract off my lower bound, so negative 2. I do the same thing, but I'm going to subtract it. 1/3 negative 2 cubed plus c. So I'm going to get 1/3 times 1 cubed plus c, so 1/3 plus c, minus negative 2 cubed is negative 8. Negative 8 times 1/3 is negative 8/3 plus c. And so we're going to get 1/3 plus c plus 8/3 minus c. Because I have to remember actually to keep the square bracket if I haven't applied the negative sign through, because I need to distribute that negative in and to the minus c, which is perfect because now the plus c and the minus c cancel, so even though we don't know what they are, they just go away anyways. And 1/3 plus 1/3 plus 8/3 is 9/3. I really want to say the answer, which is 3. So technically up here we have this equals 3. So the area under the curve of x squared from 1 to negative 2 is an area of 3. Now we're going to look at b. b is 0 to pi over 6 cos of x dx. So I'm going to have to do the antiderivative of that for the fundamental theorem of calculus. So the fundamental theorem of calculus says find the antiderivative of it, put square brackets a to b, then once you've found the antiderivative, do f of b minus f of a. So we're going to go antiderivative of cos of x is sine x. How do we know that? Because d over dx of sine, touched my arm down, of sine x equals cos x. dx technically. So cos x, the antiderivative of that, is sine x. So we're going to have sine x plus c from 0 to pi over 6. And remember, you have to show that plus c each time, even though I know it's going away. So that's the first step in the fundamental theorem of calculus. Find the antiderivative and put it from 0 to pi over 6. Then your second step is to fill in pi over 6. Subtract, fill in 0. Okay? So we're going to have sine of pi over 6 plus c minus bracket sine of 0 plus c. And we have to remember to bracket that second half because we have to subtract everything in it. So we're going to have to subtract that and subtract that. That's why we need to make sure we have brackets. So sine of pi over 6 is what y is at pi over 6, or 30 degrees, which is a half, plus c. Sine of 0 is what y is at 0, which is 0. And then I have to subtract c still. Now the c's cancel, and I'm left with 1/2. And that's my answer. And that's the answer to this as well. Okay. So if I do c, c is between the antiderivative, or the area between 0 and root 3 over 2 from the graph of 1 over the square root of 1 minus x squared dx. Now, I gave you a table of integrals that I told you should keep close to you, just like the table of derivatives. So the table of integrals, if you look at it, this 1 over the square root of 1 minus x squared is actually the antiderivative of sine negative 1x. So d over dx of sine negative 1x, and it's on your chart, equals, so when they're complicated looking, think, are they an antiderivative of an inverse? Okay, so the antiderivative of 1 minus 1 over the square root of 1 minus x squared is sine neg 1x. So our first derivative is our first step is to write the antiderivative. So sine negative 1x plus c from 0 to root 3 over 2. Then we do function notation where we fill in the root 3 over 2 first, subtract, fill in the lower bound. So we're going to get sine neg 1 of root 3 over 2 plus c minus sine neg 1 of 0. Oh, I found that spot that doesn't like writing. Plus c. Sine neg 1 of root 3 over 2 is pi over 3, because where is root 3 over 2? It's pi over 3. Plus, and we're looking in the first quadrant, plus c minus, and then sine neg 1 of 0 is at 0. And I know these are at different places, but you want to stick to one quadrant, so I always stick to the first one. Plus c. So now I'm going to get pi over 3 plus c minus 0 minus c, because I have to remember to distribute that minus sign in. C's cancel. Pi over 3 minus 0 is just pi over 3. So the answer to this integral, definite integral, which means it's a defined one on a certain value, is pi over 3. There's one little spot of my iPad that doesn't like writing on. I don't know why. It's weird. It's on the middle right. Oops. All right. Let's go to this one. So it's a defined integral because it's between two values. The ones we've done up to now didn't have any numbers on that integral symbol. So we're looking for the area under the curve 1 over x from 1 to 2, when x equals 1 to x equals 2. All right. So our first step for the fundamental counting principle is to find the antiderivative of 1 over x. And the antiderivative of 1 over x is ln absolute value x plus c. from 1 to 2. Second step, substitute in the 2 and the 1 with function notation. So we're going to do ln absolute value of 2 plus c minus bracket ln absolute value of 1 plus c. The absolute value of a number 2 is just 2. So I'm going to go ln of 2 plus c minus ln of 1. Because remember, the absolute value just turns it to a positive. And then minus c. C's cancel. And you're left with ln of 2 minus ln of 1. And you'll leave it here unless they ask you for a rounded answer. And if you're in university and they don't give you a calculator, you can't make it any further than this. So that would be your answer. All right, E is the graph of y equals 2. So the horizontal line at 2. What's the area between x equals negative 2 and x equals 3? So what would that look like? Well, we'd have a line, horizontal line at y equals 2. And we're trying to find the area between negative 2 and 3. So we're finding this. That's what we're doing every single time we do integrals. So every single time we do a derivative, we could do rate change, or we could do tangent slopes and stuff like that, which helps us draw graphs. The biggest thing that integrals give us is area under curves. They also give us volumes and such like that. All right, so let's solve this one out. So the antiderivative of 2, when you have a constant, the antiderivative was just that with an x, right? So we get 2x plus c from negative 2 to 3. Then we do function notation, so we go 2 times 3 plus c minus bracket 2 times negative 2 plus c. So I'm going to get 6 plus c minus a minus 4, so plus 4 minus c. The c's cancel, and I'm left with 10. And technically, this is 2, a height of 2, and this is a width of 5. So what's the area of that rectangle? 10. So there, it proves it. So if it's a rectangle, it's easy. You could literally just go length times width, but they're not all rectangles, right? Most of them are not. So the area is 10. Let's look at the last one on this page. So we have 1 to 3 from 1 over x cubed. The first thing I would do is write 1 over 3 x to the negative 3 dx, just because it's easier to deal with. The only one I don't change is 1 over x, because that's just ln. So the antiderivative of that is going to be add 1, so it's negative 2 actually. So we're going to get 1 over negative 2 x to the negative 2 plus c from 1 to 3. And then we fill it in. So we get negative 1/2 times 3 to the negative 2 plus c minus negative 1/2 times 1 to the negative 2 plus c. So that's negative 1/2 times 1 over 9, which is negative 1 over 18. Because 3 to the negative 2 is just 1 over 3 to the positive 2, which is 1 over 9, plus c, minus, and 1 to the negative 2 is just 1, times negative 1/2 is negative 1/2, times negative 1 is actually positive 1/2. And then we have to remember to distribute it to the c as well, so minus c. The c's cancel, and you get negative 1 over 18 plus 9 over 18, because we have to get a common denominator, put them together. So we get 8 over 18, which actually reduces to 4 over 9. So if I found the area, don't know what I just did there. This way. Sorry. So if I find the area of the graph 1 over x cubed if I graphed it, and I wanted to find the area from 1 to 3 to the x-axis, it would be 4 over 9. And it's always the area to the x-axis. Okay. Then our last page of notes for this lesson. It's a short one. My goodness. Okay. So we have to do the antiderivative of cos x, which we did already with sin x. We're just doing the same thing. So we're going to get, and if you want to try these out before me, please just pause them and then check after to see if you get them right, okay? You don't have to do them with me every single time. Okay, so the antiderivative of cos x is sin x plus c from 0 to pi over 2. And so we're going to get sine of pi over 2 plus c minus sine of 0. Not wanting to write here now. Weird. Sine of 0 plus c. Sine of pi over 2 is 1, because at 90, my y is 1, plus c. Sine of 0 is 0, minus c, because I have to remember to distribute it. The c's cancel. And I'm left with 1, minus 0, which is 1. So the area under the graph of cos x from 0 to pi over 2 is an area of 1. All right. Then we have 0 to 4, x to the power of 3 over 2 dx. So when I do the antiderivative of 3 over 2, I have to add 1 to it. So if I go x to the 3 over 2 and I add 2 over 2, I get x to the 5 over 2, right? So I'm going to end up with x to the 5 over 2. My iPad is not liking me today. Okay, x to the 5 over 2. And then I'm going to divide by 5 over 2, right? That's what I've always done. I divide my coefficient by 5 over 2. But dividing by 5 over 2 is the same as multiplying by 2/5. So I just multiply by 2/5 instead. Plus c from 0 to 4. And so I'm going to get 2/5, 4 to the 5 halves plus c minus 2/5, 0 to the 5 halves plus c. And so, okay, let's go back over this so we don't need a calculator to do this. So the 4 to the 5 halves, remember, all you can do is you can bring that number underneath and it becomes the index of your radical. So this is the same as saying the square root, which we didn't need that 2, because square root we don't have to show. Square root of 4 to the 5th, right? Which is 2 to the 5th, which is actually 32. So we don't need our calculator for this, okay? So we have 2/5 times 32 plus c minus 0 minus c, because we have to distribute that minus sign through. The c's cancel, and I'm left with 64 over 5. And that is actually the answer, 64 over 5. All right. Once again, I don't know, you might be able to hear my kids again, but I think they're playing cards now. They get excited. All right. Now this one, we have to find the area under the curve. So we have to find the area from -8 to 0, and then 0 to 8. Now if these were two pieces of a different graph, we'd have to do them separately. But this actually represents the graph x to the 2/3. So if we just find the area from -8 to 8, being our x values here, we can just use this one graph, x to the 2/3, because that is this blue graph here. Okay, if it was a piecewise function, we'd have to find the area from -8 to 0 with a specific equation, and then 0 to 8 with a specific equation, which we are going to do in the next lesson. But this lesson, this is just one graph, x to the 2/3. So we're just trying to find from -8 to 8, x to the 2/3 dx. Wow, that's messy. Okay, so if I add 1 to 2/3, so if I go x to the 2/3 and I add 1, I would be adding 3 over 3. So I would get x to the 5 over 3, right? So I'm going to get x to the 5 over 3, And then I divide by 5/3, which is the same as multiplying by 3/5. And then I'm going to add c. And then I'm going to go from -8 to 8. And so then I have to fill in the 8 first. So 3/5, 8 to the 5/3 plus c minus 3/5, -8 to the 5/3 plus c. And so 8 to the 5/3, I'm going to do this over here just so you remember. So if I go 8 to the 5/3, then that 3 is the index. So that would be the same as saying the cube root of 8 to the 5. And the cube root of 8 is 2 to the 5. And 2 to the 5 is 32. Because it's 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. So 8 to the 5/3 is positive 32. So we're going to get 3/5 times 32 plus c minus, now -8 to the 5/3 is actually the same as saying the cube root of -8 to the 5, which is -2 to the 5, which is -32. Because you can take the cube root of a negative number. So we're going to get 3/5 times -32 plus c. And so we're going to get 3 times 32 is 96 over 5, because 32 is just over a 1, so you multiply straight across, plus c, minus a minus 96 over 5, so we end up with actually a plus 96 over 5, minus c. And then the c's cancel, and I am left with 192 over 5, which equals 38.4. And it makes sense because look, aren't these equal areas, this part over here and this part over here? And we take those two areas and we add them because they're both above. So this is 96 over 5. Well, so is this. They're the exact same. So it should make sense when you sketch them. And that's the lesson for today. It's a short one. And then we're going to go over more detail. Harder ones that are definite integrals, but not hard by any means, just harder, but still very easy. Have a good day.